Welcome back to this second introductory lecture on proof techniques. In this third segment, we will introduce yet a different proof technique called proof by contradiction. The reason you might want to use a proof by contradiction is when the previous proof techniques do not obviously apply. In particular, if you're trying to prove the conditional P implies Q, and you can't do that in a direct way, and you also are not successful in proving its contrapositive, then you might want to try this proof technique called proof by contradiction. And here is how it works. In a proof by contradiction, you start by assuming that the theorem is false. And then, from that assumption, you try to derive a contradiction. Deriving a contradiction means you derive something that is not possible. Since the only assumption you made was that the theorem was false, and from that you derived a contradiction, the only problem in your proof must have been the assumption, namely that the theorem was false. And therefore that allows you to infer in an indirect way that the theorem must have been true. Because when you assume it was false, you derived a contradiction. So to summarize, in a proof by contradiction of a conditional P implies Q, you assume that P is true and Q is false, because that's the only way that the conditional could be false. That's the only counterexample of the conditional. So you start from this assumption, and if you are able to derive a contradiction from that single assumption, then by contradiction you prove that the theorem must have been true in the first place. So again, we're going to use the same theorem to illustrate this proof technique. But this time we're going to write a proof by contradiction. Now notice we don't really need that proof technique in this particular case, since we were already successful in proving the theorem using a proof by contraposition. But you could have tried a proof by contradiction first, and so let's do this one here. First of all, as always, we have a universally quantified theorem. So we're going to assume or pick an arbitrary integer and call it n. Then the key in a proof by contradiction of a conditional is to assume that its hypothesis P is true and its conclusion Q is false. So now we must assume two things, namely that n squared is even and that n is not even. In other words, n is odd. And that is our assumption for this proof by contradiction. And now what we can do is we can derive a contradiction from this assumption. Now it's a little bit vague because a contradiction is not well defined. Remember, a contradiction is any proposition that is false. For example, R and not R, for R being any proposition. R and not R is a contradiction since it's always false. So it's not quite clear what contradiction we're going to arrive at here. But what is clear is that we must start from this assumption. And we already know from previous experience that it is pretty hard to infer something from n squared being even. That's what we tried in a direct proof. So let's start from the second operand of the conjunction here, this one, and see if we can derive a contradiction. So since we just assume that n is odd, we can infer by definition that there must exist an integer k such that n is equal to 2k plus 1. Well, what do we do now? Well, now that we have an expression for n, we should be able to find an expression for n squared. And the hope here is that the expression from n squared maybe is going to be in contradiction with this other assumption that we made. So let's go ahead and square both sides of this equality and see what happens. Of course, we already did that in the previous segment, so here I'm going to repeat that step without comments. And we end up with the expression n squared is equal to 2 times this integer plus 1. So of course we can proceed as in the previous proof, namely that there exists a case such that n squared is equal to 2k plus 1. But that is the definition of n squared being odd. Therefore we can make that an inference in one step. And this is where we reach a contradiction. Can you see it? Well, all along in this proof we've assumed that n squared is even. And now we just proved that n squared is odd. In other words, n squared is not even. So we have at the same time that this proposition is true and it must be false. That is the definition of a contradiction. Since we just exhibited a contradiction, and every inference from here down was logically valid, the only problem must have been the assumption that we started with. So what the contradiction tells us is that this assumption must be false. But if the assumption is false, it means it's impossible for P to be true and Q to be false. And that is the definition of the conditional P implies Q. So again, by contradiction, we just proved that the hypothesis P implies the conclusion Q, which in this case means the hypothesis n squared is even implies the conclusion n is even, which is the general form of a theorem, except that in our proof n is a specific but arbitrary value or integer, whereas in the theorem we need to prove it for every possible integer. So of course, you know the last step, we go from an arbitrary value for n to any integer value by applying the universal generalization rule. And that concludes our proof by contradiction of this theorem. So to conclude this segment, remember that a proof by contradiction proceeds as follows. If you're trying to prove the conditional P implies Q, you assume that the theorem is false, meaning you find a counterexample and assume it's true. The only counterexample is if P is true and Q is false, and you derive a contradiction from that assumption alone, telling you that the counterexample could not have existed and therefore the original theorem or conditional was indeed true.